We've been discussing indeterminate systems, and we started with indeterminate by the first degree and used 4 methods to solve for that and boundary conditions. Then we've done approximate methods. So next up is moment distribution method. And moment distribution method is great because we can, 1, use it for any degree of indeterminacy. With moment distribution method, we assume that there is no axial deformation or that it's so small that it's negligible. Third, we're going to assume that the members are prismatic. It's the same cross-section material throughout. With moment distribution method, I'm going to write down some steps. So step number 1 is the fixed end moments. These fixed end moments are from the book's back cover. Now you will see that there's 2 columns. One of them is fixed, and one of them is a fixed roller support. We are only going to use the fixed moments. Step 2 is the relative stiffness factor. We have 2 relative stiffness factors. We have K is equal to 4EI over L, or we have K is equal to 3EI over L. There are others that exist. These are the 2 that we are going to use in this class. So when do we use which one? You know, I should rearrange these. K is equal to 3EI over L. There we go. We're going to use 4EI over L if neither side can rotate. So that's going to be a beam that's fixed at both ends, or a beam that's fixed on one end and has 2 rollers on the other side. We're going to use 3EI over L if one side can rotate. So this will be a fixed end with 1 roller, or we could have something like 2 rollers on one side and 1 roller on the other. The third step is the distribution factors. The distribution factors are going to equal to the relative stiffness factor over the sum of the relative stiffness factors that come to that one joint. Step 4 is we're going to now put one joint in equilibrium. For step 4, if we have a 3EI over L, we want to start there. After we've put that one joint in equilibrium, we're going to move half of that load to the next joint. Okay, now B if again we have a 3EI over L, the number leaves and never comes back. Step 6, we're going to move to the next joint. And then step 7, we repeat steps 4 through 6 until convergence. In this case, because we're solving for internal moments and we're acting against external loads, right? So externally, counterclockwise would be positive. So internally, counterclockwise is negative, which means clockwise is positive for the moment distribution method. Now here we have a beam with a roller at B, roller at C, and fixed end at D. It's loaded from B to C with 60 pounds per foot, and it has a point load at A of 400 pounds. Now, I have 3 different inertias here. From A to B, it's 500 inches to the fourth. From B to C, 750, and from C to D, 600. Now, I said we're assuming constant cross-section of material. Well, it's constant between the supports, so we're good here. I want to find the moment diagram for member ABCD, and I'm going to do that with moment distribution method. I like to start out here with my little diagram. And the first thing that we need are our fixed end moments. Okay, so I've got a cantilever from A to B. So if I want to start with moments from A to B, I'm going to have no moment at A, nothing at all, right? Because it's not a connector, so there's nothing at all. And then at B, I'm going to have 400 times 10, which will be 4,000 pound in feet of moment. So let's put that in kip feet 4. Now we move to section BC. I have an evenly distributed load. So going to my fixed end moments, I see here when I have fixed ends at either end and my evenly distributed load across the whole thing, my fixed end moments is WL squared over 12. So WL squared over 12 is going to be my distributed load 60 times the length 20 feet squared over 12, and that is going to be 2,000 pound-feet for either side. So that's going to be 2 kip feet. Minus 2 on the left side, and it's clockwise on the right side, plus 2. I do not have any load between C and D, so my fixed end moments are going to start 0 there because I do have connectors. No connector at A, no moment at all. Connectors at C and D with no load, so my moment starts at 0. So there's my fixed end moments for step 1 of solving moment distribution method. Step number 2 is going to be my relative stiffness. So between A and B, I have no connector at A and a fixed connection from BCD, right? Because all of those things, the 2 rollers at B and C, and then the fixed end at D makes it completely fixed on that side. So my K between A and B is equal to 0. Now B and C, I have 1 roller at B, and I have a roller and a fixed end on the C side. So that means its K is going to be a 3EI over L value. And then C to D has 2 rollers on the C side and a fixed end on the D side. So that means its K value is 4EI over L. So that means my K is 3E times 750 all over length of 20. No, I'm not going to worry about units because you'll see that they divide out when we do our distribution. Okay, so as long as all the lengths are in feet and all the inertias are in inches to the fourth, we don't have to worry about units, okay? So that means this K factor is 112.5 E, and this K factor from C to D is 160 E. Since we weren't given an E, we can assume it's the same material throughout. So our distribution factor, okay, is going to be K divided by the sum of the K's that come to that joint. So that's going to be 0 plus 102.5. So my distribution factor from B to A is 0. From B to C is going to be 112.5 divided by 0 plus 112.5, which is equal to 1. So there are my distribution factors for B. For C, I have 112.5 over 112.5 plus 160. And okay, you're noticing I'm not writing the E's because they divide out, okay? So we have 0.41 on the CB side. And then coming over here and switching this with 160, we have 0.59 on the CD side. D is a fixed end, so I don't need to distribute anything away, so its distribution factor is 0. Step 4 is putting one joint in equilibrium, and we should start where there's a 3EI. So that means I'm going to start with joint B and putting it in equilibrium. When I add positive 4 and negative 2, I am out of balance by positive 2. So I need to add negative 2 to put this in balance. So I'm going to take negative 2 times 0 and negative 2 times 1. That's my distribution factors. And that's going to give me 0 and negative 2 added to joint B. So now I have positive 4 minus 2 at joint B, and it is now in equilibrium. This negative 2 that I've added to the system, half of it's going to move over, minus 1. We only move within the same segment. Joint B is now in balance, and because it's a 3EI over L, that means that joint B will not be taking anything back. So it is imbalanced and is going to stay that way. So now let's move over here to joint C. Positive 2 plus 0 plus negative 1 means that we are out of balance equals positive 1. So we need negative 1. So I'm going to take negative 1 times 0.41. And that gives me negative 0.41. And then negative 1 times 0.59 is negative 0.59. Now when I add positive 2, 0, negative 1, negative 0.41, and negative 0.59, I am now in balance. The answer is 0. The negative 0.41, half of that does not move over because of the 3EI over L. However, half of the negative 0.59 does move over. So this is going to be about negative 0.3. By the way, I can add this together. Negative 0.59, positive 0.59. D is a fixed end and it can carry whatever load we see fit. So we can leave it at 0.3 negative. And we are now in balance using moment distribution method. We did not just want the moments on either side of our connectors, we want the moment diagram. So if I come down here and draw a line, since I already have my spacing done, moment diagram, positive, negative, and let's have you in kip feet. We're going to start at 0 because I have a free end at A, and I can't have a moment at a free end. There's nothing to react against it. But I do have that 400-pound point load. So this is going to come down here at a straight line. 400 times 10, and that gets me to 4,000 kip feet, right? Positive 4 kip feet. Positive means clockwise, which is compression in the bottom down here at 4, okay? Now we move to the other side of joint B, and we have a negative or counterclockwise 4, which is still compression in the bottom. Compression in the bottom is negative. We're going to do the middle of BC in a minute. Coming over here to C, we have a positive or a clockwise 0.59 and a counterclockwise 0.59, compression in the bottom. So this is going to be up here 0.59. And then we're left with a negative 0.3. Negative is counterclockwise. That's compression in the top. So this is going to come up here 0.3. So there's all of our points as we solve for them with the moment distribution method. Now we need lines connecting them. We know that for a distributed load, the line should be a second degree curve. But how do we solve for where that moment is at a maximum and what that value is? Well, you're right, free body diagram. So here it is, section BC. So it's 20 feet between those two connectors, and we have taken our section just after roller B and just before roller C, okay? And we know that just after roller B, we have a negative or a counterclockwise 4 kip feet. Just before roller C, we have a positive or a clockwise 0.59 kip feet moment. Okay, we don't know what our shears are. And our normal forces we're neglecting. So I could just put little X's here or zeros here, whatever makes you happy. Okay, well, I need some shear values here so that I can find some more, so I can find the distance to the maximum moment and the value of the maximum moment between B and C. So coming over here at C, I'm going to just call you VBC. I'm going to sum from my moments about C. We find that the internal shear just to the right of B is 0.77 kips. Now I'm going to take another section but this time I'm going to try to solve for the maximum moment between B and C. So how am I going to do that? Well, y'all remember when we were doing moment equations in terms of X? Well, that's exactly what I'm going to do here. So I'm going to take X from the B side. I'm going to take a section within B and C and solve for those values. Now, I don't know what the distance X is, but I know, hopefully, that somewhere between B and C, I'm going to have a maximum moment. I'm assuming this kind of a curve going on here. And at some point, I'm having a maximum moment. Now, you see here that I'm also assuming that that maximum moment is positive. We'll find out doing the math whether it's positive or negative. So coming back down here, you may remember, actually, I hope you remember, that with shear and moment diagrams, we have a point of inflection on our moment diagram where shear is equal to 0. So at moment max, the shear at moment max should equal to 0. So that means I can sum for forces in the y direction, and we find X is equal to 12.8 feet. Now that I have an X, I can sum moments. And I'm just going to call that about O for my section there. Counterclockwise, I'm adding to the equation. And I find that my moment max is equal to 0.94 kilopound feet. And that positive answer means it is acting with compression in the top. So coming up here, this is 0.94 at 12.8 feet from B, because remember that's where my origin is set up. From C to D, I have no load, so I have nothing here altering what's going to happen with my moment diagram. So that's just a straight shot to 0.03. Can we use the same method on frames? Absolutely, we can use the same method on frames. So here we have a 3-member frame, and it has a constant E and a constant I for all members. So we can go to fixed in moments. I do not have any loads between A and B, so my fixed in moments are going to be 0, as is D. I don't have any loads there, but B to C does have a load in the middle. And according to the back of the book, that's PL over 8. So that will be P 8 kilopounds times length 20 feet divided by 8. So that starts us off with 20 counterclockwise and clockwise on either side. So let's get a little sketch here going. I'm going to have to get a little creative here. So I'm going to put boxes here for my distribution factors. And what I'm going to do is for member A to B, I'm going to work up. And then for B to C, I'm going to work down. And then D and B, we'll just put that on the left side there. There are all my little boxes for my distribution factors, but I want to start with my fixed end moments. Fixed end moments and fixed end moments. You start at 0 and 0, 0 and 0. And then over here we've got a 20 and a 20. And on the B side, that's counterclockwise, negative, and positive. Now that we have our fixed in moments, we need to do our stiffness factors and our distribution of those stiffness factors. So we have AB, which has a roller at one, or a pin at one end, and then a fixed and pinned on the other side. So this is going to be a 3EI over L. Same with BC, 3EI over L. B, however, has 2 pins, if you will, on its side and a fixed end. So it's going to be a 4EI over L. So this is going to be 3EI over 15, 3EI over 20, and 4EI over 12. So that means for the AB side, at B, we're going to have 3EI over 15 divided by 3EI over 15 plus 4EI over 12 plus 3EI over 20, because I've got 3 members coming into B. On the AB side, that gives us a value of 12 divided by 41. And then if we replace that with 4EI over 12 in the numerator, on the BD side, that gives us 20 over 41. And then if I replace that again with 3EI over 20, that's going to give us 9 over 41. And I just left it in fractions this time because why not? A and C are pens, so there's going to be 100% distribution. So those get 1s. They all need to go away from the pens. Pens cannot carry a moment load. D, however, can. So it gets 0 distribution. It'll take on everything. So I have my fixed in moments and my distribution factors. So now we balance. Because BC is the only one with loads, and it's also a 3, that means we balance and take away and never bring back. I'm going to start with C. C is out of balance by positive 20. So I'm going to subtract 20. That gets me to 0. Move half of it over, which is negative 10. Now don't forget, we need to look at all 3 sides of B here. So I am out of balance by negative 30. So I need to add 30 to all sides. So 30 times 941 is positive 6.58, and then times 20 over 41 is plus 14.63. And I'm going to need to remove this so that I have room. On the B side, that is 12 divided by 41, so that's positive 8.78. Okay, now that we're in balance, I do not move half of this back here because it's a 3. Same thing here. Half of this does not move over because it's a 3. But this half of this is going to go down here because we've got a 4. So that's going to be positive 7.32. Let me see. We're going to be in balance now, right? So summing that up, we have negative 23.4 and positive 14.6. And then our 8.78 is done here, 0 is done here, 0 is done on C, and 7.32 is done here. Now I did all these so I could find the reactions at the supports. So drawing our whole free body diagram, and our moment at D, which is a positive, so that is a clockwise 7.32 kilopound feet. I have too many unknowns here, so I'm going to do a free body diagram of AB. And again, I'm going to keep the same directions, AY and AX, and we will have shear BA, normal BA, and then our internal moment here, BA, which is 8.78 positive. So that is clockwise 8.78 kip feet, and this is over 15 feet. Okay, so this is a section just to the left of B. And if I sum moments about B, we will find that AY is equal to 0.58 kilopounds, and I get a negative answer, so it's actually acting down. So I'm going to reflect that on my free body diagram here, 0.58. So let's do the same thing. Free body diagram from B to C. So here's our little chunk here. This time we have our load, 8 kilopounds. So this is the only member that has a load. 1, 2, 3, and our moment on the B side of BC is negative 23.4. So negative means counterclockwise, 23.4. And then we have CY and CX, 10 feet, 10 feet. So again, summing moments about B. We can solve for CY, which is 2.83 kilopounds, and I do get a positive answer this time, which means it is acting up. So now I can sum for my forces in the y direction on my whole free body diagram. And we find that dy is equal to 5.75 up. Again, on my whole free body diagram, I can sum moments about B. And I find that dx is equal to 1.83 kilopounds. And I get a positive answer, so it is acting to the right. I run into a problem when I sum for forces in the x direction. I have too many unknowns and I'm out of equilibrium equations because I only have 3. If I sum moments about D, I will have another equation in terms of AX and CX, but it'll be a redundant equation because, again, I'm only given 3 equations for equilibrium on a 2D frame. Without further information, we're just going to have to make an assumption. So the first assumption is that A and C carry the horizontal load equally, or we can say that A takes on all the load and C's just hanging out.